Welcome you all for the another session on module 1, which is in vector calculus. So in this session we shall discuss about the Gauss divergence theorem. It is one more integral theorem which you have to learn according to your syllabus. So here, what is a Gauss divergence theorem? And let us read the statement. If V is the volume bounded by the surface S and vector f is any continuously differentiable vector function, then triple integral over V divergence f dv is equal to double integral over S vector f dot n cap into ds. So this is a statement, and you can observe the double integral is getting converted to triple integral or vice versa. So that is possible by Green's theorem. That is an advantageous. And here n cap is the positive unit vector outward drawn normal to the S. That is a unit normal vector to the surface S. So with an examples, let us learn this. First example is, if vector f is equal to 2x square minus 3y minus 2xyj minus 4xk cap, evaluate triple integral over v del dot vector f into dv, where v is the region bounded by the planes x is equal to 0, y is equal to 0, z is equal to 0, and 2x plus 2y plus z is equal to 4. So here let us do the solution. So it is asked us to find triple integral of del dot v. So first let us find del dot v and then dot product with dv, and then we will take the limits by the given region, and then we shall integrate this three integrations. So what is del dot? Del is nothing but dou by dou xi, dou by dou yj, plus dou by dou z k cap. We all know that very well. And vector f is given. So dot product between them. This is dou f1 by dou x. So divergence of f. So divergence of f is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. Dou f3 by dou z. This is the divergence of f. So when we do so, it is dou by dou x of first term I component, that is 2x square minus 3z. Dou by dou y of the j component, and dou by dou z of the k component. So here it is given that z varies from 0, z is equal to 0, and also it is equal to 4. So we can consider from this when z is equal to 0, put z is equal to 0 here, you get 4 minus 2y minus 2x. So that are the limits for z. So straight away we can take z varies from 0 to 4 minus 2x minus 2y. So similarly, when we substitute z is equal to 0 in this expansion, we get 2x plus 2y is equal to 4. So that, in other words, we can write it as x plus y is equal to 2. From this expansion, we are supposed to get the limits for x as well as y. So here, let us take y, let us say y varies from 0 to 2 minus x. So here, y is equal to 0 has been given for us. So, and from this expansion, we have y is equal to 2 minus x. So therefore, we can write y varies from 0 to 2 minus x. And put z is equal to 0 and y is equal to 0 in the expansion here in this expansion. So we get 2x is equal to 4, which implies x is equal to 2. So x is equal to 0 has already been given in the problem. So x limits are from 0 to 2. So this is how we have to find the limits for x, y, z. So therefore, triple integral over v del dot vector f can be written as, the constant limits must be written at the outermost, then the variable which has a function of single variable must be written in the middle, and the variable which has more than one variable as its limits should be written at the innermost. So z is having two variables x and y as its limits. So z limit should be written at the innermost. Y is a function of single variable, so it is in the middle, and x is having the constant limit, so it must be at the outermost one. If we follow this order, integration process will be very easy for us. So, and del dot vector f, we have found that it is 2x dz dy dx. So these order, z is the innermost one, so we are supposed to integrate with respect to z first, and then with respect to y, and then with respect to x. So integral x varies from 0 to 2, y varies from 0 to 2 minus x, and 2x integration of dz is z between the limits z is equal to 0 to 4 minus 2x minus 2y. dy dx is as it is. So 2 can be written at outside integral x varies from 0 to 2, y varies from 0 to 2 minus x. X upper limit for z is this, and lower limit it becomes 0. So dy dx is as it is. So therefore del dot vector f over triple integration can be written as 2 times of x. We are keeping it as it is, integral with respect to x, and now we are going to integrate this with respect to y. So 4 into x we have, integral with respect to y is 4xy. 2 minus 2x square, integration with respect to y is 2x square y. And minus 2x into y, and integration with respect to y gives us 2x into y square by 2. 2 and 2 gets cancelled. So you have only x into y square by 2 between the limits 0 and 2 minus x. And this dx is as it is. So now let us simplify by substituting the limits. For where and all we have y, it should be replaced with the upper limit 2 minus x. For lower limit it becomes 0. So 2 minus x, 2 minus x and 2 minus x whole square. So we can simplify this by expanding 4x into 2, it is 8x minus 4x square minus 4x square minus 2x cube, then minus 2x, and this we have to expand by using a minus b whole square first. So it is going to be a square plus b square minus 2ab. 2 into 2, which is 4 into x square. So this is what the expansion we get. So on simplifying, on expanding and simplifying this, we get x cube minus 4x square plus 4x into dx. And then now we have to go for performing the integration with respect to x. So integration of x cube is x to the power of 4 by 4, and integration of 4x square is 4x cube by 3, plus integration of 4 into different x is x square by 2, 2 and 4, it gives us 2 between the limits 0 and 2. So when we put the limits 2 into upper limit minus the lower limit, so it gives the answer as 8 by 3. So we'll see another example. Use divergence theorem to evaluate double integral over S vector f dot n cap into ds over the entire surface of the region above xy plane bounded by the cone z square is equal to x square plus y square, the plane z is equal to 4, where f is equal to 4 xzi xyz square j plus 3z k cap. So either the question can be asked like this, or find the flux across the surface. So this, in other words, it is going to be the flux across the surface. So we have double integral over S vector f dot n cap is equal to triple integral divergence of f into dv by Gauss divergence theorem. So let us find divergence of f first. So divergence of f is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. So when we do f1 with respect to x, we get 4z into 4z plus f2 with respect to y is xz square, and dou f3 by dou z is plus 3. So this is what we get divergence of f, and triple integral over v divergence of f into dv is going to be dv is dx dy dz, and divergence of f we have substituted it here. So now we have to substitute the suitable limit. So putting z is equal to 4 in z square is equal to x square plus y square, we get x square plus y square is equal to 16. So z varies from, so let us keep this, z is equal to 4, and z we are substituting it here, we get this. So from this expansion we have to get the limit for y. So this implies y square is equal to 16 minus x square, and y is equal to plus or minus root of 16 minus x square. So that shows that y limits are from minus root of 16 minus x square to plus root of 16 minus x square. So if y is equal to 0, x square is equal to 16. Let us substitute y is equal to 0 here. So therefore, when we do so, x square is equal to 16 and x is equal to plus or minus, x is equal to plus or minus 4. So x varies from minus 4 to 4. And z, since we are starting it as a cone, obviously the cone will have an origin. The base point which will be at the origin. So with that we can take z varies from 0 to 4. So z limits are from 0 to 4, x limits are from minus 4 to 4, and y is having the variable limit. So we are writing at the innermost integral, and first we will integrate with respect to y. And these two can be interchanged also, or we can keep them as it is. So let us perform the integration now with respect to y. So 4z xz square plus 3, the entire thing is constant, keep it as it is. Integration of dy is y between the limits minus root of 16x minus x square to root of 16 minus x square into dx dz. So now substituting the upper limit minus lower limit, we get 2 times of root of 16 minus x square into dx dz. So now let us write integral 8 into, so from here we have this 2 and yeah, that 2 can be written at outside, and integral 0 to 4 minus 4 to 4 z into root of 16 minus x square into dx dz plus 2 for the first term. We are segregating this term, we are multiplying inside the bracket. 4 into z into this. 4 into 2 is 8. We are returning it outside, the same thing. Similarly, this 2 into 16, root of 16 minus x square with this along with the integration, and this 2 into root of 16 minus x square along with this 3. So we have segregated the terms and written here first term, second term and the third term. So now let us integrate it. So integration of root of a square minus x square is actually root of integration of that is a into root of a square minus x square by 2 plus a square by 2 into sine inverse of x by a. That is the formula. Using that formula, we are going to integrate this with respect to x. So when we do integration with respect to x, we had got this term. And when we come to here, so one more thing we are observing here is, so root of 16 minus x square with respect to x, and the limits are from minus 4 to 4. We have a property of integral saying root integral minus a to a, f of x can be written as 2 times of integral 0 to a if the function f of x is even. If f of x is even, if f of x is odd, the integral value becomes 0. That is a property of integral. So when we observe this results in an even function. This is an odd function and this is an even function again. So how do we check even and odd function? It is with respect to like replace x by minus x, and if we get back our function, then it is even. If when we replace x by minus x, f of minus x, if results in minus f of x, then the function is odd. So this function results in odd, whereas the first and the third one are even. So we can write minus 4 to 4 integral as 2 times of integral 0 to 4. So with that we get 16. 8 into 2 are 16, and integration of which is this between the limits 0 and 4. So second term becomes 0, and straight away we will integrate the third. Integral minus 4 to 4 can be written as 2 times. So 6 into 2 becomes 12, and z into x into root of 16 minus x square by 2 plus 8 into sine inverse of x by 4 between the limits 0 and 4. So now let us substitute the limits and simplify. This is what the terms we get. And I am simplifying further and simplifying again. So 8 into pi by 2. So or you can write it as 4 pi, and here again 4 pi. So now let us perform the integration with respect to z. Integration of z is z square by 2 between the limits 0 and 4. So 12 into 4, it is 48. Integration of z, integration of dz is z between the limits 0 and 4. So substituting the limits and simplifying, we get the answer as 704. The flux over a surface is going to be 704 into pi. So this is how we will get the answer. So let us look at another example. If vector f is equal to 2xyi plus 2yz square j plus xk cap, and s is a rectangular parallel pipe bounded by x is equal to 0, y is 0, z is 0, and 2, 1 and 3, find the flux across S. So find the flux values are nothing but the divergence problems. So flux across x is equal to double integral over S vector f dot ds, vector f dot n cap into ds. So vector f dot n cap into ds is nothing but the volume integral divergence of f. So f has been given, let us find the divergence. So as we know that dou f1 by dou x is 2y into I, 2y, and dou f2 is 2yz square. Differentiation of that with respect to y is 2z square, and f3 is xz, and differentiation of that with respect to z is x. So divergence of f is that, and the limits have been given clearly: 0 to 2, y varies from 0 to 1, and z varies from 0 to 3. Integrand is divergence of f, and dv is dz dy dx. So let us perform integral with respect to z. 2y z, z cube by 3, x z between the limits 0 and 3, dy dx. So integral 0 to 2, integral 0 to 1. So y is equal to 3. So it is 6y plus 3 cube by 3. So 3 gets cancelled. 3 square is 9. 3 into x dy dx. So integral x varies from 0 to 2. And again integrating with respect to y square by 2. And 2 and 6 gets cancelled. We get 3y square. 9y plus 3xy between the limits 0 and 1 dx. So again integrating with respect to x, we get integration of this gives us 3y square x plus 9y x plus 3y into x square by 2. So this has to be evaluated between the limits 0 and 2. So when we substitute the limits 0 and 2, we get it as 12 plus 3x into dx. So on integration, we get 12x plus 3x square by 2 between the limits 0 and 2. And substituting the limits, we get the answer as 3. So double integral, the flux is given by f vector f dot n cap into ds is equal to 30. So that is about the problems on flux or the divergence theorem. Thank you all.